Before beginning with the derivation of backpropagation algorithm, we must know the chain rule of calculus, as the backpropagation algorithm applies chain rule of calculus. Suppose we have two real valued functions f and g, and y is g of x and z is f of y. Then the chain rule states that derivative of z with respect to x is equal to derivative of z with respect to y multiplied by derivative of y with respect to x. This rule can be further generalized to the case of vectors. Suppose x is belonging to a m-dimensional space and y belongs to n-dimensional space, and g maps from m to n-dimensional space and f maps from n-dimensional space to a real valued function r. So then partial derivative of z with respect to xi is given by summation of partial derivative of z with respect to some yj and multiplied by partial derivative of yj with respect to xi. This is taken a summation over all j. So the next equation is just the vector notation of the above equation, which is equal to the gradient of x is equal to multiplying the Jacobian of the matrix G, that is curl y by curl x, with the gradient of y. So the backpropagation algorithm consists of performing such Jacobian gradient products for each of the neuron in the network. Now we see the learning algorithm has got two phases, propagation and weight updates. In the propagation phase, first we propagate the outputs or the inputs to the next level to generate the output values. At the output level, we calculate the cost or the error term, which is then propagated from the output activations back through the network to generate the deltas or the gradients for all the hidden and the output neurons. Next phase is the weight update phase. Now for each weight, we follow the two steps in order to update the weights. The weights output delta or gradient and the input activation are multiplied to find the gradient of the weight. And the ratio of the weight's gradient is subtracted from the weight. This ratio is calculated by multiplying it or the gradient with the learning rate eta. Now the derivation is as follows. We assume that we have a single output neuron, and using the squared error function, the error value E is equal to t minus y square. Here E is the squared error, t is the target output for the training sample, and y is the actual output of the output neuron that we get as a result of the experiment. So now for each neuron J, we calculate its output using the following equation. The neuron J applies an activation function phi on the net input to that neuron. Now the net input is equal to the weighted sum of the outputs of the previous layer neurons, that is WK into OK. Here WKJ is the weight of the connection between the neuron K in the previous layer and this neuron J, and OK is the output of the neuron K in the previous layer. So now this activation function is linear and differentiable. Usually we use sigmoidal function, which is equals to 1 upon 1 plus e raised to the power minus z, and its derivative is equals to phi of z into 1 minus phi of z. Now we need to find the derivative of the error at the output term. So we find the partial derivative of E with respect to the weight Wij using the chain rule of calculus. Since E is a function of output of the neuron J and the output is a function of the net input to that, neuron, and the net input is further a function of the weight wij. So using chain rule, we have partial derivative of E with respect to wij is equal to the product of partial derivative of E with respect to the output oj into partial derivative of oj with respect to net j into the partial derivative of net input to j with respect to wij. Now calculating the last factor, that is the partial derivative of net input to j with respect to wij. We have the formula for net input to j is equals to wkj into ok for all k. Now this term ends out to be oi. Oi is the output of the previous layered neuron whose weight is wij. If the neuron is in the first layer, after the input layer, oi is just equals to xi or the input I. Now calculating the next term, that is partial derivative of oj with respect to net j. The derivative of the output neuron j with respect to its input is simply the partial derivative of the activation function, since oj is equal to activation function of net j. So we have already seen that partial derivative of activation function is equals to phi of z into 1 minus phi of z. In this case, z turns out to be net j, so it is equal to phi of net j into 1 minus phi of net j. Now phi of net j is equals to oj, so this turns out to be oj into 1 minus oj. Now considering the last term, that is partial derivative of E with respect to oj. Now if that neuron j is the output neuron, then oj or the output of that neuron is simply equals to y. In this case, we will simply put the formula for E, that is 1 by 2 into t minus y square. So this turns out to be y minus t. But if we have j not in the output layer but in some of the hidden layer, then finding the derivative of E with respect to oj is very less obvious. We assume that u, v up to w, these are the neurons that take input from the neuron j. That is, these are in the layer next to the layer containing the neuron j. In this case, the error E would be a function of the net inputs to u, v and w. That is, it would be a function of the weights going from the neuron j to the next layer. So we'll calculate in this form. Now taking the total derivative with respect to oj in a recursive equation for the derivative is obtained. Here we have obtained that the derivative of oj can be calculated if all the derivatives of oi in the next layer. What are oi? The neurons that receive the input from the neuron j. If the derivative with respect to oi are known, only then the derivative with respect to oj can be calculated. So summing all these terms, we have the partial derivative of error term E with respect to the weight wij is equals to oi into delta j, where delta j is the first two terms, which is equals to oj minus tj into oj 1 minus oj if j is the output neuron, and the next term if j is the input neuron. This was the propagation phase. Now in the weight updation phase, to update the weight wij using the gradient descent, we choose a learning rate eta. The change in the weight is added to the original weight. It is equal to the product of the learning rate and the gradient multiplied by -1. This -1 is added to update the weights in the direction of the minimum of the error function. As we can see,